Okay, thank you everyone for having me here today, and especially to kick off 2025 to talk about integrating electricity and hydrology disposal. So I'll share with you in this talk a few lessons that I've learned over the years in context of integrating climate change specific. And some of the things that I've learned were unexpected. In some cases, you know, like get bigger, and in other cases, the landscape is drying up. And knowing the difference is really the crux to designing and building climate resilient. He did a land acknowledgement, but I'm going to do another one because this is one that I've learned recently that I actually play. So I'm presenting to you this talk on the land known as Mokingston, where the Bow meets the Elbow River in native Blackfoot on Treaty 7 land. And today we know this place as the city of Calgary. And I acknowledge the ancestors of these lands and waterways in the original spirit of the Treaty 7 land, which the Treaty 7, which is to protect and preserve the land and the waters. So what is my goal for this HGS talk? Really that everyone, so I know I'm not involved, and you guys are of a variety of geotech, and that everyone walks away from this talk with a new or maybe a renewed curiosity for how climate change might impact scopes of work in hydrology or otherwise, depending on where the projects are located on the landscape. To get there, it's going to be a hike. So hike in the woods. I'll start with what is climate change and how you model it. So we get a little bit of a climate change primer, if you will. Then we'll talk about how climate change is impacting hydrology. Then how we make decisions in the face of uncertainty. And then I'll end with practical applications in consulting, where I'm going to highlight these lessons that I learned. And I warmed up. Right. Okay. Climate. What is climate? Climate is a summary of weather. Weather conditions over a specific geography and time period. It helps us understand what we can expect from the sky. Climate is usually presented descriptively or as statistics like that of those conditions. And when we describe the climate of Calgary, we might describe it qualitatively as humid continental climate, the eastern side, and subarctic climate for the western part. And that's largely due to the difference in elevation from one side of the sea to the other. The climate can generally be described as warm, tropical summers with freezing, dry, and extremely variable. Thank you to Wikipedia, did a great summary, a table summary for you. We can also describe climate quantitatively in the form of a table, like characterizing metrics of interest, like your average temperature or your daily mean temperature, your precip rainfall, and relative humidity. And the climate is typically averaged over a period that we call a climate normal. That's usually about 30 years. Some for thought recently, the IPCC has been recommending that we make the change to the period that we call normal from 30 years to 20 years, because the climate is now becoming too variable that 30 years is no longer with. We can also describe the climate graph in the form of a climate graph with precipitation that you see here in bars, and you've got the mean, minimum, and maximum temperature that you see over either the seasons or in this case, you have the month, year. The reality is that most of these climate descriptions rely on some version of a monthly or a seasonal average or totals of temperature and precipitation. The idea of global warming is based on calculating single average temperature across the entire planet from all the observations taken across the Earth. When you look at the annual average over the record worldwide weather observations that date back to about late 1800s, we can identify things like trends or deviations in that. And understanding what the average is helps us take a pulse of the temperature of the planet. We can also look at the changes geographically to identify places where the air is much warmer or cooler than the historical period. Using these maps, we can identify changes in the trend in climate at a particular location. And really, for the work that we do, we should care more about changes at a particular location than what the global average is doing. As the atmosphere is changing due to human emissions and other socioeconomic factors, the averages, ranges, the extremes are, and even the geographical patterns are changing. And in some places, it might not be necessarily noticeable, potentially maybe in the equator, but as you move further north, those changes become more apparent. And the distinction is important to make because in some places, the past can be strong in the future. Climate models are developed to help us make sense of the climate that's changing. And many current models couple the influence of the oceans and the atmospheric processes. The domain extends much below the surface of the ocean way into the atmosphere. And some models, more recent models, are being called Earth systems models, and they incorporate things like the carbon cycle. And the domain of global circulation models is divided into these squares covering all parts of the Earth. And these grids, when we're talking at the scale of global climate model, we're talking about 1 or 2 degrees on one side. So that's ranging between 100 to 300 kilometers. And vertically, you can have as many as 30 to 50 layers stacked on top of each other to characterize all of these processes. So here are a bunch of equations that I probably can't even solve myself anymore. But these equations of conservation of momentum and energy and mass and water vapor are all being resolved on all the individual grid cells and iterated over time. And so we call models physically based climate models. You can imagine that the computing energy, that power that's needed by global circulation models is quite high, especially when we're estimating the climate starting, say, from maybe the 1950s all the way to the end of the century on a grid scale. And so that precludes really high resolution in the GCMs that we have, which is why GCMs are typically on the scale of 200 kilometers on one side. So here, there we go. Perfect. Thank you. So here's a GCM in terms of how big the grid might be, a relative size. And so at that scale, it can be really hard to get information of projected climate for projects at the scale that we work in. And so there are a higher resolution climate model called regional climate models. And so those are typically on the scale of they could go at flow at 10 kilometers squared. And frequently, RCM can run independently of global circulation models. But the good thing about these regional climate models is that they can be used to also further downscale the GCM projection. So typical outputs of global climate models include things like temperature and precipitation. And using a physically based RCM model, often nested in GCM, can help increase the resolution of the global climate model outputs. And so often downscaling is needed because at the scale of a GCM, for example, there are certain processes that you just can't capture. So you can think about something like a convective storm, that's on the scale of 50 kilometers, for example. There's no way that you're going to be able to capture that in a GCM. So using tools like physically based downscaling, which would be by using a regional climate model, or other approaches like statistical downscaling, where you develop a relationship between variables, allows you to refine the global climate model outputs into a finer resolution. But at the end of the day, we've heard this before, that all models are wrong. Some are useful. If you don't control for confounding variables, they'll mask the real effect and mislead you. But if you control for too many, your choices will shape the data and you'll mislead yourself. And somewhere in the middle is hopefully the sweet spot, but that'll make you double wrong. So stats are a farce and the truth is unknowable. But this is just to make a little bit of fun, but at the end of the day, it's true, all models are wrong, which is why there are so many climate models. To estimate future climate, modelers have to make certain assumptions about possible changes in CO2 throughout the model run that affect temperature. There are a suite of emission scenarios, each that correspond to an assumption about global warming by the end of the century. And these different scenarios account for things like yes, so there's a suite of emission scenarios that correspond to an assumption of global warming by the end of the century. So for example, so this is based on the latest assessment report that was published a couple of years ago. And so you've got, for example, SSP 5-85, so that's one that heard a lot about. So the 8.5 is related to the amount of energy that we are assuming at the end of the century. And that scenario, that's the red one at the end, is typically related to assumptions of fossil fuel development. And somewhere middle of the road, we've got the emission scenario of SSP, which stands for socioeconomic pathway 2-45. That's typically the middle of the road, where we're assuming a smaller degree of warming by the end of the century. And typically, scenarios in the range of 5 to 7 are the ones that we expect without additional climate policy. And right here is really tricky when we incorporate climate change as part of our work, because we have to make assumptions about what the end of the century is going to be like, based on information that we have right now. And so often we try and incorporate multiple climate models, multiple emission scenarios. And something to keep in mind also, a fact that I learned recently, is that in 2024, so we talk about the temperatures by the end of the century, and 1.5 degrees of warming since the pre-industrial period is a number that we hear a lot. And in 2024, the average of the planet, we that 1.5. That's interesting. On information. Always keep at the back of our mind as we move forward in time. Okay, so for some of my jam is hydrology. And so when we talk about climate change, I'm curious about climate change. I want to learn a lot about it, but I'm not a climate scientist and certainly not a climate modeler. But what I do is that I use outputs of models as inputs into things like hydrological models. And so one important question that we have in hydrology is, if the atmosphere continues to warm, will the water cycle intensify? And this question is an important one because if it does intensify, then it would lead to an increase in the frequency and magnitude of extreme events like flood. And what you see here is a schematic of the water cycle where you've got processes in black and the direction of the change in red due to climate change. And the theoretical basis for the intensification of the water cycle is due to this equation, or is summarized by the relation called the Clapeyron relationship. That means that the atmosphere can hold more water as it gets warmer. And that's been quantified to 7% for every degree of warming. And so that means that with potential changes in the strength of atmospheric circulation, precipitation events are going to become more intense and could even, the term is exhibit super Clapeyron scaling, which sounds super nerdy, but that means that the atmospheric circulations are going to get even faster. So you might end up with even more than 7% that you might expect. The intensification of the water cycle can impart changes to the flood hydrograph shape that impacts project work. So this is me drawing a cartoon to kind of illustrate those changes. And here what you see is a typical stream flow in a Canadian watershed, where we've got time, the different season on the x-axis and stream flow on the y. And so in the fall and winter, these could be, convective storms where you get some small peak in response in your river. And then you get a big peak here that responds to the snow melting, the snowpack that had accumulated over the winter, melting throughout the spring. And then, the recession limb throughout the summer. And in the summer, you might get some convective storms as well. That's your typical flood hydrograph in a Canadian river. And in context of climate change, your peaks can decrease if your snowpack is not accumulating as much over time. But on the flip side, it could increase if hydrological processes in your watershed are changing. For example, if you get a rain on snow event, you've got your snowpack and you're adding water to that. Changes in the magnitude of flood has a direct impact on the frequency magnitude curve that we use to estimate things like the design flood. The design flood in Alberta is the 200-year event. And the timing of flooding can change. What we're seeing in a lot of rivers across Canada is that the timing of snowmelt is earlier than it used to be in the past, because the atmosphere is warmer. And this change has implications for things like mine water management and decisions about when to raise the dam. And here, another change that we might expect is an increase in the duration of the flood. So it starts perhaps at the same time, but the peak isn't as long, but it's sustained for a longer period of time. And this has implications for geohazards like landslide, for example, especially if you've got a river flowing at the toe. And for other fluvial processes like bank erosion that might encroach on a highway or a railway. Yeah, this one's one of my favorite ones. I'll talk about in more detail a bit later too, but another process, and another change could be a change in process that is driving flooding in your watershed. So what used to be potentially snow melt in the spring, now it's changing to another process that wasn't as big as it was before. And this might be things like atmospheric river in the southwest of British Columbia. We've seen that climate change can cause both an increase or a decrease in flooding, depending on the location and the time of year. Floods result from a combination of factors, including rainfall, snow melts, rainfall and snow melt and temperature. And these are what we call processes that are happening, in the sky. Climate related, those are the flood drivers. And depending on those changes, it will influence your flood activity. You might get more or less flooding, depending on how these changes are combined together. And as you go from things that are happening in the sky to once they hit the ground, then you increase your uncertainty. So for example, we've got fairly good understanding of how temperature is projected to change. But as you go from temperature to precipitation, you're in uncertainty. That uncertainty keeps increasing as you go from precip to flooding. And then once you get the processes where sediment is involved, like steep creek, your uncertainty increases, and then never mind about landslides. The International Panel on Climate Change introduced this qualitative framework for reporting uncertainty and assessing the overall confidence in projections derived from future climate unfolds. And depending on the amount of evidence and agreement, so the evidence would be, for example, the number of GCM that you're able to look at during your analysis. And the agreement would be, are they agreeing together or are they not? And that framework was translated to a likelihood scale from virtually certain, where you've got, say, lots of different GCMs that you were able to look at, and they're all aligned, to exceptionally unlikely. So this framework is used to help us say things like in Canada, that there is high agreement that Canada's climate has warmed about 1950 and will continue to warm throughout the years. There's also general agreement that precipitation will increase across most regions of Canada. So the models disagree on the amount and timing of increases. And for example, we can say things like, here, like in the Arctic, for example, that we're virtually certain in an increase in temperature, that we've got medium confidence in that how that relates to an increase in precipitation. We can quantify those. And of interest to me particularly is that it's highly likely that these changes will result in an increase in extreme flooding. And so somewhere else, that we've got this big plus sign here. We're looking at Missouri, the Milk River, the St. Mary's River, in southern Alberta, Missouri area. We're virtually certain of an increase in temperatures. That one we typically have really good confidence in. We've got low confidence in how that relates to precip, but we've got medium confidence in decreases in stream flow. So 10 years ago, the International Panel on Climate Change published projections to the end of the century about warming that ranged from 0.9 or 1 degree to about 5 degrees relative to the pre-industrial period. And so these are the results of So the AR stands for assessment report number 5. So those were the projections. So you can see, you've got the different lines, the yellow, red, blue, and brown are different assumptions of emission scenarios about related to climate policy and socioeconomic factors. So you can see that you've got a peak, so this is the probability density function, and you've got a peak and you've got a big spread. And so at the time, that made it really difficult to make decisions about what value that you want to incorporate into your design. And the AR6 projections, which is the latest generation of climate models, if you will. The good news here is that we, the royal we, have been able to reduce that uncertainty. So we've been able to narrow the range of warming. And that's in part because we've got now international commitment on emission reduction, which is helping us constrain that uncertainty into the future. Things like, and so that's one thing, we've got international commitment, but we've also been able to track what our CO2 emissions has been over time. And what we're seeing is that global emissions are still increasing, but they're doing it at a much slower rate. And there are 18 countries that are seeing sustained reduction in emissions. So that's certainly some good news from that perspective. And we've got also the lower cost of this technology. That can help us lower our emissions. And so you've got here the different emission scenarios. So in the previous slide, I was talking about how SSP 2-45 is kind of like the middle of the road scenario. And in this latest assessment report, the scenarios that kind of have fallen off the bandwagon are the ones that are related to fossil fuel development without additional climate policy action, which is really interesting. And so when I was reading this paper, actually it came out like last summer, and I was reading it this week, and as I was reading the comments about how our uncertainty with different emission scenarios has been decreasing. I get a notification on my phone from BBC, so you guys maybe get it on your phones too, where Trump vows to the Paris Climate Agreement and drill. And so even though we make these assumptions about what our carbon emissions are going to be like at the end of the century, we can still get curveballs that change the projection in the future. And at the end of the day, with all of that uncertainty, we still have to make a decision. So even though we've been really good at reducing the uncertainty in climate projections over time, it's still present, but we still have to make a call. And so how do we do that? How do I do that? And there is some guidance for climate change adaptation in engineering and geoscience practice. In 2018, Engineers Canada released a national guideline pertaining to principles of climate adaptation and mitigation. So that document is really great, but it doesn't establish any legal standard. And there is no, it doesn't include or constitute professional or legal advice. Like, hey, just a guidance if that you might want to consider. That as professionals, we're mandated by provincial and territorial law by engineering and geoscience regulators. In BC is UTC, and in Alberta, I should know, I'm a member. APEC, BC, no, APEC, Alberta. Yeah, and for in BC, what they've done is really great. Actually, it's crux. Might be even the only jurisdiction that have stuck their neck out to say, hey, general guideline is to increase by 10 or to 20% your peak flow to account for climate change. That's in BC, that would be to the 200-year flood. So that's great. It's the first time that we've been mandated to do something about it. Now, the 10 to 20% I'll talk about in my application. And other more recently, best practices for climate change impact assessments on peak flows for the Canadian Bridge Design Code were published by the Canadian Standards Commission. So this document is not a whole picture. What it does is it talks about an approach, a recommended approach moving forward that includes the development of scaling factors so by scaling factors, I mean, how much bigger is the 200-year flood going to be in the future? So recommends a data set of scaling factors for rivers across Canada. So that's not available right now, maybe in 5 years or so. But as engineers and geoscientists, we have a duty of care. Our failure to design and build infrastructure sufficient to withstand known climate change related impacts may be subject to liability for damages under the common law, torts of negligence, nuisance, among others. So what does that mean? Is that while there may not be explicit guidance for climate change integration into projects, we still have a responsibility to protect the environment and to protect the public. And one thing that's on my mind that I've done a bit of research on, but I haven't found yet, which is probably good news, but I haven't seen yet an example where a professional has been taken to court, or an engineer or a geoscientist taken to court for failure to incorporate climate change as part of their design. I haven't seen a case yet. Okay, so in this last part of my presentation, I'll share with you some of these lessons learned over the last 5 or 6 years through Project Exam. And a lot of my work is based on a frequency magnitude relationship. And so I thought I'd describe what that is. And we build a frequency magnitude relationship that helps inform how often floods of a certain size happen. So it could be floods, but it could be any natural phenomenon. So what we typically do is we've got a time series of data. This happens to be meters cubed per second, but it could be anything over time. The biggest flood in this case per year. And then we put it in different bins. And so half of my data, and you group it and you order it, half of my data is less than 40 cubic meters per second. And here you've got 20% of my data is less than 60. And you do that for all of your data. And the red dot, that forms your empirical or my empirical distribution. And when we talk about flooding in Canada, our records are not typically long. We usually have maybe 30 years on average of data. And that's probably good enough to tell you what your 30-year flood is, maybe your 50-year flood, but we don't often care about those. We care about the 200-year flood. So how do you go from what the data is telling you to those higher return period flood events? And that's where the fun begins. That's where stats come in and distributions come in. So you try and fit different models. You're like, okay, well, which one is it? And sometimes you're lucky, you've got one model, like, yeah, that's a pretty good fit, but really you have no idea. So sometimes you just take an ensemble of a whole bunch of different models. But those statistical models help you extend beyond the observed data to estimate things like the 200-year flood. And so that's going to be the basis for some of the examples that I'll share with you. Okay, so as part of floodplain mapping projects, and this is in BC, this is for the Thompson River watershed. And this project was kind of a meta-analysis in disguise. we had to estimate the climate adjustment for a bunch of watersheds, or sub-watersheds within the Thompson River. And what you see here is that, raining a little bit, but the climate adjustments range from 0 to up to 75%. And so putting that in context to the EGDC guidelines that we're saying, hey, you know, increase by 10 to 20% depending on what the past is telling you. And so what this is showing is that, yeah, you know what, that's probably not appropriate. And those numbers, you know, they're probably wrong, but what we're showing is that the range is actually quite big. And these numbers were estimated using stream flow projections that are available in BC. And the assumption in this case was based on a radiative forcing of, so it's 8.5 watts per meter squared by the end of the century. So that's kind of equivalent to that fossil fuel development scenario, which is definitely on the high end, but it gives you a sense of the range. And so the learning piece here for me was, yeah, the magnitude is probably wrong, but what it's telling me is that where I am on the landscape really matters. And so I'm going to share with you 2 examples and the bookends. So we'll talk about a 0% increase, what that looks like, and a 75% increase. So this example, this is the Thompson River in Kamloops. So that one is right kind of in the middle of the Thompson River watershed. And floods in the Thompson River watershed occur in the spring due to snowmelt. You have your snowpack that accumulates throughout the winter, and then as it gets warmer, it floods over a period of several weeks with the peak sometime in the spring. And what we did is leverage stream flow projections that were available at that location. And we calculated the 200-year flood over time. So what we did is we calculated using the statistics that I talked about before, the frequency magnitude relationship. And we did it over chunks of 30 years of time. And then we used a moving window to calculate how that 200-year flood was changing. And that's what you get here. That's the scaling factor. How much bigger or smaller is the 200-year as we go into the future? And what we see is that climate change impacts on flooding is not linear with time. And at the end of century is not necessarily the worst case. So here, what we ended up doing for this project is in context of floodplain mapping, we didn't increase the 200-year flood. And that was considered conservative in itself, as opposed to the end of the century. Now, the next site, for me, was probably one of my watershed moments in my career. We all get some of those. The Coldwater River is located in southwest BC, and it was subject to a lot of flooding following an atmospheric river that happened in November of 2021. And here is some satellite imagery that shows you the atmospheric river. And what you've got up here is location of Merritt. And that atmospheric river dropped high intensity rainfall over a period of 2 days. And what followed from that was a lot of flooding in Merritt and a lot of landslides, a lot of changes in the river in terms of the planform and bank erosion. And following that, PGC was hired to support some of the recovery efforts. And so that's where I came in to estimate the frequency magnitude relationship for the Coldwater River. That is actually still ongoing. Almost done. So here's an example, that's a photo in Merritt. There was a big avulsion, so that means that the river jumped its bank, created a new channel, and they had to build an emergency dike to contain the water. And some bridges were washed away, some roads were washed away, so that information, the design flood was used to help rebuild merit. Okay, so I got to work, and the first thing that I did was look at what data was available for the cold water river. And one of the first things I noticed was that flooding is happening at different times in the year. You've got flooding that's happening in spring due to snowmelt, but you also have events that are happening in the fall due to rainfall. And actually, if you look closely, the 10 biggest rainfall events are rainfall related in an otherwise snowmelt dominated watershed. And that distinction is important because the standard practice is to put all of these floods together and analyze them as a single population of events. What we did was separate. Like, what do the distributions of the rainfall and the snowmelt floods look like? And what we saw was that the rainfall related floods is convex versus the snowmelt related floods is concave. And to us, that was justification to say, you know what, we're probably mixing two populations of hydrological processes here. And so what we did is we defined both distributions separately and we combined them out. So the combining process, there's a mathematical equation for it, but really what you do is randomly pick an event from this bin, this model, and this model. You pick the bigger one, and then you put it on the right side. And you do that a whole bunch of times to define your probability distribution. And what this shows is that the flood magnitudes that are on smaller bands, so your lower return period events, are typically rainfall related. But as you get to higher return period events, like rainfall, or like the 200-year flood, those are typically rainfall. And that was a big mind opener for me. Where understanding what hydrological process is driving the flood is really important. So that was one thing. Two, that it wasn't standard practice. So there was a lot of pushback to estimating the design flood of this way. But one of our other asks was, one, please estimate the design flood, and two, integrate climate change. And so what this approach really helped us do is integrate climate change in a physically meaningful way. So in that watershed, we could leverage stream flow projections. And what we saw was that rainfall-related floods are actually projected to increase over time. But if you look at the snowmelt-related floods, it's kind of intuitive, right? You're going to get less snowmelt, less snowpack accumulation. So those floods are projected to decrease in the future. And so by separating those two processes and building your FM curve, you can incorporate climate change in a physically meaningful way. And yes, and so by doing that, because the projections in rainfall are shown to increase, that's where the climate adjustment of 75% came in. As we know that those floods, the design floods, is rainfall dominated. And so what we did is we scaled these distributions over time to get a scaling factor of 70. And again, is the 75% the number? No, it's probably not the number, but the answer is that the number is. So there's another aha moment, if you will. So whether climate change will impact the design flood really depends on the time horizon. And so, for example, if you're doing routine hydrotechnical assessments that you do maybe every 5 years or something like that, then maybe it's not necessary to incorporate climate change. And what you're seeing here are two FM curves, the historical and the climate adjustment. So if you're looking in the near term, say 10 years, and this is for a specific watershed, that in mind, for the Pocatello River, I picked a watershed where I thought I would have the biggest change. And so if you look in the near term, the next 10 years, no way, it probably really doesn't make a difference, so don't worry about it. But if you're looking at building new infrastructure, like, I don't know, a bridge or a new highway or something that you're gonna want to maintain a certain standard of operation in the long term, like 70 years, then you're starting to see a difference. And so to help inform the decision about whether or not you incorporate climate change, thinking about how long your infrastructure or your project timelines. Okay, another one, this is probably one of my favorite ones, is the past may not be representative of the future. I moved to Calgary about 2.5 years ago. And when I did, I was really curious. I knew that the water supply came from the Bow River, and I was curious about what was happening in the Bow River. And this is one of the longest records in Canada. It's the Bow River at Banff. And what you see here is a time series of that annual maximum flood that typically for the Bow River occurs in the spring. And what we see is that there's a decrease in the mean over time. And you can run some simple stats to find out if that's statistically significant. And in the case of the Bow River, it is. So we know that there's that the peak flow has been decreasing over time. But what about the future? Can we rely on that trend in the future to make decisions about how the city of Calgary should invest in things like mitigation structures, for example? And that's a difficult question to answer. And what comes to help us make that decision are hydrological models. And what we do is we take these outputs, temperature, precipitation from global climate models, and we use them to drive another set of models that we call hydrological models and help us simulate rainfall. And so if we look at those models, hydrological models, and there has been in the past 10 years or so, been a lot of work done in the Bow River. What we see is that depending on the study, some are showing, oh, well, it's going to go up, and other studies are showing, well, actually, it's going to go down. And so that's in part because the Bow River, the headwaters are in the mountains, and snow dynamics are really hard to simulate. And so that makes it difficult to get research to align on a final answer. And so in the case of the Bow River, at Banff and the city of Calgary is that they're planning for a potential increase in the flows in the Bow River, despite the fact that historically floods have been. And what's happening with climate change is that in some cases, like we talked about, the processes that are driving flooding could be changing. So of course, we'll all remember the we were there. I wasn't there, and I remember it, 2013, the flood event. And so what's happening is that the hydrological process, the atmospheric processes are changing in terms of the time and the magnitude. And so what happened here was that you had a snowpack. It could have been a typical year where you had a snow melt. Then you had a synoptic scale event that brought a lot of rainfall. And so that combination of two processes that were previously separated in time are now aligning, resulting in even more flooding. And so that's what happened in 2013. And so the city now has invested a lot of money in flood mitigation, despite the fact that the past is telling us that flooding has been. Okay, and in my abstract, I said I was going to talk a little bit about geohazards. So floods are a geohazard. That's only one of them. And Jack could probably stand up and talk to this slide better than me. But another type of geohazard are debris floods. And So these are geohazards that we typically find in steep mountain or watersheds. And the difference with floods is that they increase in sediment concentration. And what's interesting about these geohazards is when it comes to climate change. And so we were talking about how we're fairly confident about temperature. We get to precip, and we know even less about the projections of how the magnitude and timing of that's going to change. And then we get to flooding, and these even more uncertainty. And we keep going down the process order. When we get to steep creeks, we're like, oh, we're still kind of increasing that uncertainty. And that's in part because of the sediment concentration. And what's interesting about steep creeks is that it could go both ways, right? Depending on how much material you have in your upper watershed. That's related to the sediment supply. So if your watershed, the steep watershed has a lot of sediment, if you think about climate change, it's going to be warmer, it's going to be more precip, more frequent, higher magnitude events. If that supply of sediment unlimited, you're going to get bigger and bigger and bigger events, bigger flows of events generated in your watershed. That's not always the case. The sediment supply in your watershed could be limited. So in the case where you're going to have more frequent rainfall events, actually the magnitude might decrease over time because you're flushing all of that sediment in the watershed. And so when we're building geohazard management programs for regional districts or pipeline operators or things like that in context of climate change, making the call on how much sediment is available in your watershed can be really tricky. It takes a good eye that is not my eyes, but and a lot of remote sensing information to make that decision. And so a summary of what I've learned so far in my quest to understand climate change and incorporate it into hydrology. The good news is that uncertainty in climate change projections is decreasing. So that's a good news story here. The uncertainty increases as precipitation hits the ground. And floods can get bigger or smaller depending on where you are on the landscape. Climate change impacts on flooding is not linear with time. Sometimes we assume that, oh, end of century is going to be the worst case because it's going to be the warmest. Well, that's not necessarily true. And climate change impacts on the design of flood really depend on the time horizon of interest. Are you going to be updating your analysis in 5 years? Or does your design need to stand for the next decade? And lastly, past isn't necessarily representative of the future. And so what am I still curious about? At the beginning of the talk, I was saying that the goal of this talk is for us to walk away with a renewed or a new curiosity about how climate change might impact our society work. And so for me, I'm still curious about how climate change will impact flooding in watersheds where more than one hydrological process is at play, like rain and snow. Are the stars going to align such that we're going to get bigger floods? Or are they not? Floods going to get smaller time. And to do, yeah, there. That's it. So what I leave you is, what are you still curious about when it comes to climate change, and how does it impact your work or your skills of work?